Okay, welcome to Module 4, Endpoint and Application Development Security of the Security Plus or Network Security Fundamentals series of courses. So tonight, we are going to go over multiple topics. Hopefully by the end of the lecture, you will be able to describe different threat intelligence sources, list the steps for securing an endpoint, and explain how to create and deploy DevOps or security development operations, right? So that's the new field. It's getting very hot these days, and it's good that you're touching it as a part of this lecture. So suppose you were to uncover a zero-day vulnerability that nobody else knew about. So what could you do with it now that you are in control of that zero-day vulnerability? As we discussed, and you remember, zero-day vulnerability is a vulnerability that nobody knows about it, and it's just have been discovered. Of course, you could be a broker and sell your knowledge of the vulnerability to a billing buyer. Actually, governments often serve as buyers of zero-day vulnerabilities to protect their citizens or attack their enemies. Other billing buyers are like third-party acquisition platforms who actually buy and then resell the vulnerability information to a government or software developer. Very billing buyers are also threat actors who would craft their own attacks based on the vulnerability that you just discovered. However, a more responsible option would be for you to privately disclose the vulnerability to the developer of the software application or the entity that you found the vulnerability on. This is going to allow them to fix it so that it's not going to get compromised by malicious actors. Not all zero-day vulnerabilities are discovered by individuals like you or me, right? Many organizations have internal security teams who look for vulnerabilities in their own code and in programs from other developers that they have in place. When they find a problem, they privately contact the software developer with the information so that the developer can patch it. The question here is, what happens if developers drag their feet and do not patch the vulnerability within a reasonable period of time? Delaying can actually keep the door open for a threat actor to find the zero-day vulnerability and then consequently exploit it. Faced with a conundrum of trying to give developers time to create a patch and the public's right to protection from those attacks, organizations have came up with disclosure deadlines, right? Or the time that the software developer is given to patch a vulnerability before it is publicly disclosed. This disclosure deadlines generally range from anywhere from like 45 to 120 days, right? One thing that we can go back and look into is when in early 2020, Project Zero announced a trial tweak to their disclosure deadlines, right? And the limit is a still 90 days, right? So Project Zero sometimes found that software developers were rushing to fix the zero-day vulnerabilities to meet the 90-day deadlines. And because of that, because of the rush that they wanted to have in order to fix everything within 90 days, flawed patches were being introduced into the code again. So basically, what was happening is pushing people to get the vulnerabilities addressed quickly, in result of which now the patches which were going out were not complete and good enough, not tested enough, and therefore actually adding to the issues and the problems that you have after application of those patches. At one time, organizations were reluctant to share information about the attacks on their networks and endpoints. They didn't want to create the concern in the public, basically trying to avoid bad publicity, right? Which these kind of disclosures can bring in. If a company comes out every week and say, hey, you know what, we found this vulnerability in our networks, people most possibly are going to lose their trust, and the image of the company may kind of get damaged. And that's the reason that in the past, it was considered bad publicity and therefore not happening. However, today, this really is no longer the case. Organizations are pulling their experiences and knowledge gained about the attacks on their networks, right? And even a broader security concerns about the networks into a community, right? So sharing this type of information has become one of the most important aids to help other organizations shore up their defenses. One type of shared information is the evidence of an attack. Most organizations monitor their networking environments to determine what normally occurs. They use this data that comes out of monitoring to create a database of key risk indicators or KRIs. A KRI is a metric of the upper and lower bounds of the specific indicators of normal network activity. So they look into their network activity and they create a baseline. If the baseline is exceeded by certain threshold, then a risk indicator is going to be there, right? So a KRI exceeding its normal bounds could be an indicator of a compromise, which we call it IOC. An IOC shows that malicious activity is occurring, but is still in the earliest stages of an attack. So think about a computer in the network that the owner of the computer only checks internet on a regular basis, and they just send out a couple of emails a day, maybe to their best friend saying, hi, hey, I'm at work. It sucks to be working today. It's too hot. I want to be out there, blah, 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 right? And all of a sudden, the traffic of this specific endpoint jumps up to all the way about, let's say, 2 gigabits per second. This is basically an indicator of a compromise. Something should have been happening that the baseline of this computer actually is now different. So making the IOC information available to others can prove to be of the high value, as it may indicate a common attack that other organizations are also experiencing or will experience soon, but they don't know anything about it yet. So if we found it in our network, it's always good to provide that to the community in the industry so everybody can get an understanding of it. This type of aid is called predictive analysis. Basically, other companies, based on the aid received from us, can predictively analyze and see if that attack actually is going to happen on their network as well or not, and create a defense against such attacks. So there are multiple sources of intelligence that can provide the IOCs to us, so that based on those IOCs, we can analyze what's going on in our own network or within the application we have. The two categories of the threat intelligence sources are open source and closed source. The open source information that we touch at first is basically coming from the computer industry, and the terminology is coming from development industry in the past, right? Initially, the open source terminology was referring to software for which the source code was open for anyone to examine, like Linux, right? Over the time, open source was used to refer to anything that could be freely used without restrictions, such as an open source film or open source curriculum or open source music, anything that can be freely accessed, right? So open source threat intelligence information that is freely available often is called open source intelligence, or OSINT. This has become a vital resource to the industry. This information is often collected and then disseminated through public information sharing centers. A typical sharing center in the United States Department of Homeland Security Cyber Information Sharing and Collaboration Program, or CISCP, is what a lot of industry resources are using nowadays. The CISCP enables actionable, relevant, and timely unclassified information exchange through trusted public-private partnerships across all critical infrastructure sectors in the United States. With the DHS, or Department of Homeland Security, serving as the coordinator, the CASCP enables its members, which we call them partners, to not only share threat and vulnerability information, but also take advantage of the DHS's cyber resources, which some of those, as you can see, are listed over here. We do have the analyst-to-analyst technical exchanges, basically in which partners can share and receive information on threat actor tactics, techniques, and procedures. We actually refer to this as TTPs, right? Tactics and procedures, right? Threat tactics and procedures, and also the emergencies and emerging trends within the industry. CISCP analytical procedure, as you can see, or analytical product, sorry, as you can see, is a portal that can be accessed through which partners can receive analytics of the products and the threats already discovered. Also, they provide cross-industry orchestration, so partners can share lessons learned and their expertise with peers across common sectors. Last but not the least is digital malware analysis, which in this case, suspected malware can be submitted to be analyzed by CISCP and then used to guarantee malware analysis reports to mitigate threats and attack vectors all over the entire industry. Okay, so there are two concerns, right, around the public information sharing centers that actually mostly are addressing the privacy of the shared information and the speed at which information is shared. So these two, privacy and the speed, are the major concerns. So a concern about using public information sharing center is that of privacy, and it always comes to mind first, right? An organization that is the victim of an attack must be careful not to share any specific information or sensitive information when providing IOCs and attack details. So the information should be really scrubbed off of any kind of sensitive information. As a safeguard, most public information sharing centers have protections in place to prevent the disclosure of any kind of proprietary information that they may have. Second is the speed problem, right? The speed concern. So threat intelligence information must be distributed as quickly as possible to the partners. To rely on email alerts that require human to read them and then react the attacks, usually we take too much time, right? They need to receive the emails, read the emails, make the decision, start the reaction, right? So as an alternative, an automated indicator sharing, or AIS, can be used instead. So instead of emails coming in, you're going to have an AIS in place, which enables the exchange of cyber threat indicators between parties through computer-to-computer communication, not the email communication. So push notifications, application notifications, and such, right? Threat indicators such malicious IP addresses or the sender address of the phishing email can be quickly distributed to enable others to repel these kind of attacks without even waiting for the emails to be received, analyzed, and acted upon. So two tools facilitate this AIS. One is a STIX, or structured threat information expression, which is a language and format used to exchange cyber threat intelligence. All information about a threat can be represented with the objects and descriptive relationships between the objects. So STIX information can be visually, and this is a nice part about it, can be visually represented for a security analyst to view or stored in a lightweight format so that can be used by the computer itself. The other tool is the TAXI, or Trusted Automated Exchange of Intelligence Information, which is an application protocol for exchanging cyber threats intelligence over Hypertext Transfer Protocol, or HTTP, in the secure format, HTTPS. And you guys possibly are going to remember that we said HTTP plus SSL or TLS is going to give us HTTPS. So taxi itself defines an application protocol interface or API and set of requirements for taxi clients and servers, which most of the industry leaders are using nowadays. So when it comes to the closed source, basically we have the opposite of the open source. It's proprietary, meaning it's owned by an entity that has an exclusive right to it. Organizations that are participants in closed source information are part of a private information sharing center. So we call them private information centers because nobody besides the members can have access to it, in contrary with the open source that we just reviewed. These restrict both access to the data and participation. So even the participation is restricted. Whereas private sharing centers are similar to public sharing centers in the manner that they share threat intelligence information, insights, or any kind of best practices, tools. Private sharing centers actually provide tools to remove or defend against the threat, right? So all in all together, you can be a member of a closed source and take advantage of it, or you can just use the open source that is freely available out there, right? All candidates also must go through a vetting process and meet the certain criteria that closed source information system is mandating. So now that we discussed open source and closed source, let's talk about the actual sources of threat intelligence. There are several sources of threat intelligence, and all of them are useful to us, right? Those include, first and foremost, vulnerability databases. What is that? A vulnerability database is a repository of known vulnerabilities and information as to how they have been exploited. These databases create something we call feeds of the latest cybersecurity incidents. Common cybersecurity data feeds include some like vulnerability feeds that provide information on the latest vulnerability, and threat feeds that outline current threats and attacks that are available out there in the world. The adversary tactics, techniques, or procedures, again, TTP, is a database of the behavior of threat actors and how they can orchestrate and manage different attacks on the hosts. Threat maps, what those are. I mean, to some extent, these are fun visual tools to look at, but a cybersecurity threat map illustrates cyber threats overlaid on a diagrammatic representation of geographical data, right? So we do actually have a threat map over here, right? So as you can see, we have the geographical data and we do have the threat maps. You can actually really easily go to these threat maps and see what's happening, who is attacking who, and the representation is actually fun to look at. At the same time, it's very awakening on which countries usually are involved in attacks on which countries, right? So they help in visualizing attacks, providing a limited amount of context because these are really in the abstract level, right? And show the source and source of the attack, target of the attacks, the type, and historical and near real-time data about the threats. But again, you're not going to find very detailed information in these type of tools. The other type of tools are file and code repositories, right? File and code repositories are another source of threat intelligence. Victims of an attack can upload malicious files and software code that can then be examined by others to learn more about the attacks and craft their defenses. There are several entities of U.S. government, include, well, now I cannot even talk. There are multiple U.S. government entities included in the backing of this type of tools. You're going to know one of the most famous ones, right? The Federal Bureau of Investigation, or FBI. the Cybersecurity and Infrastructure Security Agency, or CISA, and the Department of Defense, or DoD, or US Cyber Command. These are mostly active in posting files and code repositories. So often samples of recently discovered malware variants are also uploaded to the virus depositories and malware depositories, which one can go up there and gain the knowledge that they need to defend their network from. We also have the dark web, right? That's the underground of the internet. So you know that the web has 3 levels, as you can see here. Let me just show you this. These are the 3 levels of the net. So you have a clear web, you have a deep web, and you have a dark web, right? So the dark web is like the deep web in that it is beyond the reach of normal search engines, but it is the domain of the threat actors. Using a special software such as Tor, Onion, or I2P, Invisible Internet Project, you can mask your identity, and then you can conduct any kind of malicious activity, such as selling drugs, stolen personal information, buying and selling malicious software that people use for attacks, buying vulnerabilities, and so on and so forth. Actually, some security professionals and organizations use dark web on a limited basis to look for signs of the information of the or critical information of their company that is being compromised, being sold in there, and it's available in there, and literally just predicting an attack by looking at what is going on in the dark web. If there is no question so far, let's do a knowledge activity check. So what is the significance of a KRI exceeding its normal bounds? Looking for answer from you guys. Anyone?
E.
It could be an indicator of a compromise, right? That's correct. So if a significant change happens in the KRI, you possibly are being compromised at that point, and you better just do something about it, right? So far we talked about the threat actors, vectors, and where you can go to find the information. We talked about dark web actually as well. And now I want to talk about securing endpoint computers, okay? So it is important to understand that despite the fact that the endpoint devices like your smartphone, your iPhone, your Android phone, tablets, let's say Apple Watch, whatever you have, like a Garmin watch or any kind of those wearable fitness trackers, they usually receive a lot of bulk attention. The workhorse of technology remains the personal computers, right? So I think everybody agrees that computers that we have on our desks are actually the workhorse of our technology world. A research showed that more than 260 million computers are sold annually only in the United States, compared to the 160 million smartphones sold each year in the United States. While all endpoints must be protected from attacks, endpoint desktop and laptop computers must be secured because they are concerned to corporate networks and the industrial data that actually runs the infrastructure of the country. They contain data stored locally, and they can be used as a springboard to attack to the other endpoint. So we discussed lateral movement previously. If your desktop computer is compromised, then an attacker can easily use it as a lateral movement foothold in order to compromise any other computer which is connected to that one. So securing endpoint computers primarily involves 3 major tasks: confirming that the computer has started securely, so a secure boot, protecting the computer from the attacks, and then hardening it from for even greater protection. So first and foremost is confirming the boot integrity. One of the steps that is often overlooked in securing endpoint computers is to confirm that the computer has started without any malicious activity taking place. Ensuring secure startup involves the Unified Extensible Firmware Interface, or UEFI. I'm not sure how many of you guys have seen that terminology, UEFI, on your BIOS. If you have played with your computer BIOS in the past, you should have seen that abbreviation UEFI, right? So that's there to kind of like provide the boot security for you. Anyone before, let me ask you, the class, anyone has the experience of using with Unified Extensible Firmware Interface, or UEFI? This comes from the early BIOSes. No one?
No.
Okay. So have this as a buzzword in your mind. You can see the abbreviation right here. And later down the road, when you actually start working with the computers and setting up the BIOSes, this is something that you're going to see, and this is going to kind of like ring a bell in your mind, right? So let's actually talk about this. Early cowboys and work hands were known for wearing tall, tight-fitting boots, right? These boots had a tab or a loop at the top through which a tool called the boot hook could be inserted to assist pulling the boot up, right? In the mid-1800s, the expression "pull yourself up by your own bootstraps" was used to describe an impossible task of lifting oneself off the ground by pulling the bootstraps. The phrase later came to mean, and today, actually, the meaning of it has changed to improve your situation by your own efforts without any external help, right? Computers adopted this language, the bootstrap language, to describe the process of starting a computer when it has been powered off. Because a computer is unable to rely on external assistance when powered on, starting a computer is called booting up or just booting. So now you see where this boot process comes from, right? The booting process on early personal computers, both Apple or PCs, used firmware called BIOS. Has anyone heard about BIOS? Basic Input Output System?
Yes.
Good. So UEFI actually is substituting the BIOS. Maybe now it makes more sense, right? The BIOS was a chip integrated into the computer's motherboard. Usually a battery was accompanying it to make sure the information is not being lost. So on the early computers, you were able to remove the BIOS battery and kind of like reset everything on the computer, including the boot password. So when the computer was powered on, the BIOS software would awaken and perform steps in legacy BIOS boot. So primarily the BIOS would first test various components of the computer to ensure that they were functioning properly. This is where you would have received beeps when something on your hardware was not in good condition. Like if your RAMs were out of the socket, you were receiving multiple beeps showing that, hey, something is wrong on the motherboard. Let's get down there and fix it. Next, the BIOS would reference the master boot record, or MBR, which is a specific computer partition table, and then read the operating system from there. Finally, the BIOS would pass the control to the installed bootloader, which then would have launched the operating system. So originally, BIOS firmware was stored on a ROM, or a read-only memory chip, on the motherboard itself, supplemented by a CMOS, complementary metal oxide semiconductor chip, which was stored to keep the changes that you make to the BIOS as a small memory, or let's say a small storage for the BIOS. Later, computer systems stored the BIOS content in flash memories, so it could be easily updated. So early computers couldn't have any kind of BIOS update. They were just as company was decided for them to be. But when the flash memories came to the play, now the biases were able to be uploaded. To add functionality, an improved firmware interface was developed to replace the bias. And that's what we call it a UEFI, or Unified Extensible Firmware Interface. UEFI actually provides several enhancements over bias. This could be the abilities that it adds, basically accessing the hard drives that are larger than 2 terabytes. Like with the old biases, you cannot have any hard drive that is larger than 2 terabytes, period. That's the extent that bias can address, but UEFI can do that. It also provides support for an unlimited number of primary hard drives partitions. So in the past, we had a limit, but now you basically can just partition down your hard drive to as many as you like, right? Without any problem. Also, networking functionalities in the UEFI firmware itself are way advanced, and they provide ability to remote troubleshoot the computer. And UEFI also has a more advanced user interface for configuration and information. Basically, on the UEFI, as you can see here on this slide, you do have a multiple sources to play with the setup and configurations, and almost all of the UEFI biases, they come with a graphical user interface, as you see right here. In the past, when you were booting your computer up, you were just needed to hit on one of the keys. Early days, it was a delete key. Later, they changed it to F4, F8 on different machines. It's different. Different vendors use different keys to just enter the BIOS, in which after entering the BIOS, you had a command line interface, or a CLI, which was allowing you to apply changes, configure, and so on and so forth, right? But now, as soon as you enter the BIOS, you're going to land on this graphical user interface. Your mouse is going to be enabled, which in the legacy BIOS, you didn't have it. But now in UEFI, you have the mouse enabled, and you can basically move around, click on the items you want to change the configuration for, and basically just have a full-fledged control over the BIOS. So a significant improvement that UEFI brings over the BIOS relates to boot security. The ability to update the BIOS and firmware also opened the door for a threat actor to create malware to infect the BIOS itself. These are called the BIOS attack. It would exploit the update feature of the BIOS. Basically, they can come in and change the BIOS into whatever they want it to be. So then your computer is not going to securely boot, but it's going to boot up to what the malicious actor wants it to boot to. So because the BIOS resides in firmware, and an infected BIOS would then persistently reinfect the computer whenever it was powered on, BIOS attacks were difficult to uncover and hard to disinfect. Every time you boot the computer, BIOS is going to infect your hard drive. You go in, you get the anti-malwares into work, remove the malware, remove the issue, just to restart and let the BIOS infect the entire thing once again. And that's kind of scary, right? That power is actually kind of scary. Boot security that we're discussing here involves validating that each element used in each step of the boot process has not been modified. This process begins with validation of the first element, which is the boot software. Once the first element has been validated, it can then validate the next item, such as a software driver, right? And so on until control has been handed over to the operating system. This is what we call it, the chain of the trust, right? So you may hear that terminology, the chain of the trust, in multiple locations. So each element relies on the confirmation of the previous element to know that the entire process is now secure. But the question is, how does the chain begin? What if a threat actor were to inject malware prior to a start of the chain of the trust? Then what? If the starting point is a software, it can be replaced or modified. That would then compromise each element of the chain. So to prevent this, a chain of trust requires strong starting point. Any questions so far, guys? No? Good, good. So let's continue. The strongest starting point, it's going to be what? Let me ask the class. If we want to have a super strong starting point, what would you choose to be the starting point? You can also cheat off of the slide.
Hardware.
Exactly, right? So the strongest starting point is always a hardware, which cannot be modified like a software, right? This is known as hardware root of trust. Security checks are rooted in, or let's say they begin in hardware checks, because this chain of trust begins in a hardware verification. Each subsequent check can rely upon it, which we call it boot attestation, basically, right? There are many techniques to get this done, but those are out of the scope of the discussion we have over here in this specific time. So I'm going to leave it for later, and we're going to go and talk about protection of the endpoints, right? So far we talked about how to protect the boot process. Once boot security has been established, the computer endpoint must be actively protected. Now you booted, you're sure that the boot process was flawless. The chain of trust was there. Now let's actively protect the software and operating system. The protection can be done through software installed on the endpoint, such as an antivirus software or an anti-malware, a web browser protection tool, and anything like a monitoring and response system, IDS, IPS systems, depending on what technologies you want to use. So when it comes to an antivirus, which is a known entity, basically, most of you guys are familiar with that. We have to say one of the first software protections was the antivirus, or as you can see, the terminology here refers to it as an AV. This software can examine a computer for file-based virus infections, as well as monitor computer activity and scan new documents that might contain a virus. Scanning typically is performed when the files are opened, created, or closed. However, some antiviruses scan the entire disk regularly, even when the files are just at rest, right? So if a virus is detected, options generally include cleaning, deleting, quarantining, or logging the file and reporting those to the AV. So these logs that are created with AV products can also be provided in the threat intelligence, right? So basically, you can simply just send them to any of these repositories that we discussed, open source or closed source repository we discussed at the beginning, and those logs are going to serve as threat intelligence. Many of the antivirus products use signature-based monitoring, also called static analysis. The antivirus software scan files basically by attempting to match the known virus patterns against potentially infected files. So this is called string scanning. Other viruses or other variations of antiviruses include wildcard scanning, which basically just looks at any kind of information that may be matching the signature throughout the entire file. And also we do have the mismatch scanning, which in mismatch scanning, you allow a set of numbers of bytes in the string to be any value regardless of their portion in the string. That means you can notice any kind of changes that has happened to that specific file through comparing it with a string of the bytes from the original, the original file that you always have or is known to you. However, a newer approach to antiviruses is dynamic analysis, as you can see on the last line of the slides, right? Which this one uses a variety of techniques to spot the characteristics of a virus instead of attempting to make matches. The difference between a static analysis and dynamic analysis detection is similar to how airport security personnel in some nations screen for terrorists. A known terrorist attempting to go through security can be identified by comparing his face against photographs of known terrorists, which is a static analysis. They already have photographs, they compare it with the faces, and statically they can see, okay, this person looks like this photo. So how about a new terrorist with no photograph in the repositories? So this security personnel can look at the person's characteristics, holding a one-way ticket, maybe not checking any luggage, not having anybody accompanying them, showing extreme nervousness, right? And any kind of indicator like that, right? Anything out of norm, anything out of ordinary can be questioned here, and basically dynamically that terrorist is going to be detected. So that's what a dynamic. Is there a question? Yeah, guys, please mute yourself if you're not talking. Nancy, please mute yourself. Thank you very much. Let's come back here. Now let's talk about anti-malwares. So instead of only protecting against file-based viruses, and remember we talked about file-based and fileless viruses in module 2, right? So what an antivirus does is looking at the file-based viruses, right? Anti-malware is a suite of software intended to provide protections against multiple types of malware, such as we discussed, ransomware, crypto malware, Trojans, or other types, right? Some anti-malware softwares protect against a spam that has evaded the corporate email gateway, and they monitor emails for spams and other unwanted contents at the same time. Anti-malware spam protection is often performed using a technique called Bayesian filtering. The software basically divides email messages and looks at those which have been received in two piles, right? Spam and non-spam. The filter then analyzes every word in each email and determines how frequently a word occurs in the spam pile compared to the non-spam pile. A word such as the, right, would occur equally in both piles and then given, let's say, a neutral 50% ranking. A word such a report may occur frequently in non-spam messages and would receive a ranking of 99 or even 100, right, for being a non-spam word. While a word like sex may receive a -1 or even a 0, which means maximum possibility of being in a spam, right? And this is being marked as a spam word. Whenever an email arrives, the filter looks for anything that can actually show the sign of a spam. And if more than 15 words, or let's say 20 words, depending on the configuration, has the highest probability to be in a spam, then the entire message is going to be calculated as a spam. So another components of an anti-malware suite is the anti-spyware. The anti-spyware helps prevent computers from becoming infected by the spywares themselves. One common technique is to use a pop-up blocker. A pop-up, basically, actually, let me ask you this. Can anyone explain what a pop-up is?
It's a new window in your internet browser that opens sometime in response to an action you took on purpose, and sometimes even if you don't want it.
Yeah,
and they can be misleading at times or dangerous.
Exactly. I couldn't explain it better than what you did. So great job. That's the definition of a pop-up, right? So using a pop-up blocker, users can often select the level of blocking ranging from blocking all pop-ups to just the ones that are from a specific website, right? These pop-up blockers come with your anti-malwares, and they help you protecting yourself against the possible malicious activity that the pop-ups can bring into the play. Next, we want to talk about protection of the endpoints from web browsers perspective. Web browsers have a degree of security that can protect endpoint computers themselves, right? This security includes secure cookies and HTTP headers. These are the two important aspects of it. So secure cookies, when you look at HTTP, which is an internet-based protocol, and actually is the foundation of all data exchanges on the web today. I mean, you cannot find, I want to correct that. You barely can find any internet communication which is based on it's just not based on HTTP. It is a client-server protocol, so that requests are initiated by the recipient or client, which is your computer, and usually through your web browser to another web browser on the server. One of the limitations of HTTP is that it is a stateless, meaning unlike a stateful protocol, which remembers everything that occurs between browsers, this one basically forgets what happened, right? And as a stateless protocol, it forgets what occurs when the session is interrupted or actually ends. This means it can be actually compromised. 3 ways that the stateless protocol HTTP can mimic a stateful protocol include either using a URL extension to the state that is sent as a part of the URL response. So basically the URL defines the state, or using a hidden form of fields, which is the state that is sent to the client as a part of the response and then returned to the server as a part of the form's hidden data. Or it actually can use the method called storing user data information, or what you know as a cookie, right? So user data can simply be saved into the same computer as a cookie. So next time that user sends any kind of request, that cookie sent back to the server has everything that you actually need to provide to server to receive any kind of response from the server. Question here is, have you ever seen errors about, hey, you need to clear your cookies, or messages from your browser that tell you, do you like to allow the site to copy cookies into your computer, or anything related to cookies on your computer in the past? Anyone have that experience? Did you allow that? Did you think about what is going on? Sorry, can you please mute yourself? Hey guys, if you're in a noisy environment, please do not open your mic, because that basically disrupts our discussions and all that. But anyway, the cookies that you receive can be the source of malicious activity. Websites use several types of cookies. It can be first-party cookies, right? And I want to talk a little bit more about cookies before I move forward. So it can be first-party cookies, which are created from the website that a user is currently viewing. Whenever the user returns to this website, the cookie is used by the site to view user preferences and better customize the browsing experience. That's why every time you go back to Amazon, whatever you have browsed before is known to Amazon, and Amazon knows, okay, you have done these things, you're interested in these things, let me show more of those, right? These cookies often are stored into the hard drive of your computers, right? Some websites attempt to place additional cookies on your local hard drive. And those additional cookies come from third parties that advertise on the site, right? Or the third parties that want to know more about your purchase trend, right? So if you look for something on Amazon and then you go to eBay or any other website, you may see suggestions of the same item coming to you from this third-party website now. These are the third-party cookies, right? No matter how we name them, no matter how we categorize them, cookies can pose security risks as well as privacy risks, right? First-party cookies can be stolen, and therefore your information is going to be stolen with that. Third-party cookies can be used to track the browsing or buying habits of a user and hence violating their privacy. When multiple websites are serviced by a single marketing organization, cookies can be used to track browsing habits on all of the client sites. If you have noticed, even some applications take advantage of that tracking through cookies. And this is something that actually I have noticed in iOS now. When you want to download an application, the application is going to ask permission to track your activities. And you can say, no, don't allow the application to track my activity. And this means you're not allowing the application to drop any kind of information into cookies and basically steal your information. The rule of thumb is, hey, as far as possible, don't let any cookie be stored for tracking your activities, because these can easily turn into any kind of security risk or issue. So last but not the least are the monitoring and response systems that can help you harden the security of your workstation. There are three types, as you can see on the slide. We do have the host intrusion detection systems, or HIDS. We do have the host intrusion prevention system, or HIPS. And then finally, we have the endpoint detection and response, or EDR systems. First one is a software-based application that runs on any endpoint and can detect that the attack has occurred. The primary function of the HIDS is automated detection, which saves someone from sorting through log files to find the indication of an unusual behavior, which we just discussed about it, right? HIDS can quickly detect evidence that an intrusion has occurred. And an HIDS relies on agents installed directly on the endpoints. If the agents are not installed on the endpoints, then your HIDS is not as effective as possible, right? So these agents send information to the HIDS about different aspects of the system, like system calls, file system access, input outputs, and such, to create a very good understanding of what's going on in that network. Also, SIMs and SOARs that we discussed on week 1 are good examples of kind of being an HIDS. So the second one, or HIPS, or prevention system, as the name's implying, it's an intrusion prevention system, which not only monitors and detects malicious activities, but also attempts to stop the malicious activities. These systems monitor endpoint activity and immediately block any kind of malicious traffic going in and out. They are following specific rules, like the firewall rules that you have. Activity that a HIPS watches for includes something like events that attempts to control other programs or terminate other programs, events that try to install devices, device drivers, install applications, and similar to that. So when a HIPS blocks an action, it then alerts the user so that an appropriate decision about what to happen is being made by the user. So they tell you, hey, an activity was going to install something on this computer. We stopped it from happening. Would you allow that? Those of you who installed Windows 10 themselves, you have seen the user account control of the Windows 10 actually is acting as a HIPS. So every time you want to install an application or an application wants to apply any changes to your computer, it pops up and tells you, hey, this application is trying to apply changes to a computer. Would you allow that? Or this is something that you want to stop from happening. I'm not sure if you guys have seen it, but those of you who maintain their computers themselves should have seen many instances of user account control intervention. Third one, the EDR. These are the tools which are really similar to HIDS for the monitoring and very similar to HIPS or HIPS for preventing of an attack. So EDR tools are considered more robust than both in the sense that an EDR can aggregate data from multiple endpoint computers to a centralized database so that security professionals can further investigate and gain a better picture of events occurring across multiple endpoints instead of just a single endpoint, which you see in IDS, right? This can actually help determine if an attack is more widespread across the enterprise and if more comprehensive and higher level action needs to be taken. Second, EDR tools can perform more sophisticated analytics that identify partners and detect anomalies. This can help detect unusual or unrecognized activities by performing baseline comparisons of normal behavior of those type of codes or applications. So we talked about the threat intelligence. We talked about how to secure endpoints. Now I want to talk about hardening the security of the endpoint. So after boot security has been established and the endpoints have been protected, the next step is to harden the endpoints for further protection. Hardening of an endpoint involves patch management, as you can see, and also OS protections. Right? These two are the most important parts of it. So patch management is one of the most important steps in securing an endpoint computer. And a lot of time, companies have very robust and detailed patch management plans. Because as we discussed, the patch itself may introduce vulnerabilities. So companies may come up with the plans to apply the patches first in a QA environment or in a test environment before they actually apply the patches to the production environment and such. We don't want to go very deep into how to design a patch management plan, but usually patch management plans are really detailed, especially when it comes to enterprises. So modern operating systems like Linux Red Hat or Apple Mac OS or Ubuntu and Linux or even Microsoft Windows 11, 10, whichever version you can imagine, they frequently distribute patches. So a growing number of applications and utility software developers are also distributing patches for their products like Adobe Photoshop, I don't know, the games you play, anything, like the patches are coming out nowadays for almost everything. They're not only limited to the operating systems, right? These patches, however, can sometimes create new problems, such as preventing custom applications from running correctly. Organizations, as I said, that these type of applications usually go through different steps of testing the patches before actually applying those. Some operating systems like Microsoft 10 have specific options for their patch enforcements, right? So as you can see on the slide, you can have forced updates, no selective updates, more efficient distributions on the patches. So basically you have a variety of control over which type of management plan you want to have in place in order for your patches to be effectively applied. On the operating system side, one thing that I mean, actually, there are three important things that you can do in order to harden an operating system, right? Those three important things are take care of configuration, take care of configuration, and take care of configuration. Bad configuration management is basically the Achilles heel of an operating system. The security of an operating system depends upon the proper configuration of its built-in security features. Modern operating systems have hundreds of security settings, like even thousands of security settings, depending on which operating system you're touching. A typical OS security configuration should be including disabling unnecessary ports and services so that those cannot be abused, disabling default accounts or passwords. I mean, in the past, even Microsoft Windows had the guest account enabled by default. So anyone who was sitting on your computer and had enough knowledge to understand that the guest account is available could have compromised your computer with just getting into it, right? And these days, those are disabled by default, right? And then employing the concept of least functionality. It is really, really important. Actually, in military, we do have two concepts to look into. One is need to know basis, and the other one is least privileges, right? And over here, we do have employing of least functionality aligned with the same concept. So basically what we want to happen is every application, every user should be limited to the least level of functionality when it comes to their access into the system. So that in case of a compromise, and the compromise, it's not necessarily the bad actor being the person who has the access, right? It can be their account being compromised, and then because they have functionalities available to them, which is way beyond what it should be, then in this case, that account can turn into a foothold that can be used against the entity to get it compromised, right? So what you see on this slide is preventing access to registry editing tools, right? Anyone who has a Windows can simply go to the search box and put in regedit, where you can bring up registry editor, and that's the heart of the Windows, right? You can easily go ahead and compromise a Windows with changing the values to the keys. It's out of the scope of this discussion, but that's a fun thing to learn, how to change configuration of your computer through accessing registry editor. Definitely you want to restrict access to this guy, right? Any kind of confinement tool is recommended to restrict your malwares. Any malware on the system should be sandbox guaranteed. Using application whitelisting, you want to block those. And nothing in your computer should be able to move easily, right? Everything should be controlled before they actually move from point to point in your computer or from an application to application in your computer. As you can see here, what we see is you have multiple application 1, 2, 3, right? That they are on top of the operating system. And the files and settings of those is centrally being managed to harden security against any kind of access to the hardware, which actually happens through your drivers, which are a part of operating system, applications installed on top of operating system. You see how direct access can easily happen over here, right? But over here, as you can see, we have a sandbox, the application which we are suspicious about with its files and settings now is isolated in this sandbox, right? And now we can monitor the traffic that goes out and into that to make sure we do have a full control over what's going on in there. Any questions so far?
By sandbox, do you mean this is different than a virtual machine?
It is different than a virtual machine, but the concept is the same. This actually is also virtualized, right? That the virtual machines that you know, which are installed on top of a VMware, right? Or on top of a VM box or virtual box from Oracle, those are what you just create the entire operating system in there. Sandbox is more aligned with the concept of a container in which all of your application file settings and whatever is related to that application is in a container contained with the resources they need from the operating system, communicating with the operating system. They can continue doing the job properly, but in case they're acting maliciously, you can simply just delete the sandbox and throw them away. So very close to that concept, but not exactly the same.
Got it. Thank you.
Sure. So let's do a knowledge check, guys. So who can answer this for me?
Whitelisting?
Any other answer?
I agree.
Yeah. Whitelisting.
Everybody says whitelisting.
D, letter D. Yeah.
Legacy boot. Look at this. Just actually back here, I believe I talked about this. I think I talked about this earlier. Yeah, we talked about this earlier, guys. So basically, you can use whitelisting, quarantine, or sandbox in order to confine a malware. Legacy boot was to protect a secure boot. Remember, we talked about this prior to the concept of malwares at the beginning.
Oh, that's right.
Right? That's really not where a malware is existent, because when you're booting, you're not still having the operating system up and running. Okay. So now we want to enter the world of security DevOps, right? So confirming boot integrity, protecting endpoints, and hardening endpoints are all very, very essential security steps that we have to take to secure an endpoint. But an additional element that is also critical is creating and deploying secure applications, because if the applications that you have are not secure by default, like if someone with malicious intentions have developed those applications, then that basically is not detectable, and it's even worse than worse, right? So there are many types of attacks that can happen when you have an unsecure application. And that is being discussed under the concept of secure software development, right? So think about an application with permission to go around your computer and change directory whenever it wants, write into different directories, read from different directories, and so forth. And this application, when it's power, is going to have access to your file system. The root directory is a specific directory on a web server's file system, and users who have access to the server are usually restricted to the root directory and directories and files beneath the root directory, but they cannot access other directories. For example, the default root directory of Microsoft's Internet Information Services, or IIS, is under the C, under a folder called INET pub, and then you have the www root, so it's a specific folder. Users have access to this directory and subdirectories beneath this one, if given permission, right? But they should not, or they do not have access to other directories in the file system, such as, let's say, the system 32 under Windows directory. A directory traversal attack takes advantage of a vulnerability in the web application program or the web server software so that the user can move from the root directory that they have access to other restricted directories. The ability to move to another directory could allow an unauthorized user to view confidential files or even enter commands to execute on a server, which we call it command injection. a directory traversal attack is also a very powerful attack in providing a foothold so that basically you can conduct a lateral movement between the rest of the system. So as you can see on the slide, there is another dangerous weakness in an application that can create vulnerability in computer memory or buffer area. So as we talked about buffer overflow and stack overflow attacks in the past, right? If a poor memory management is happening, then any kind of these attacks in memory can happen. Overflowing the stack, overflowing the memory, and taking advantage of the vulnerable situation that it causes, right? What you see over here is the access we were discussing to, right? So if I have access to this folder, I'm going to have access to whatever comes underneath that, subdirectories. So through directory traversal from here, I can go up to Windows and from there to Win32 and compromise everything in Win32, which is called traversal attack. So when we do application development, guys, there are multiple phases. And what you see here as general concept is what we call a waterfall methodology. In waterfall methodology, the stages and phases come one after each other in a sequential way, right? So we design, we develop, we test, we stage, we release, and then we go back again, we find errors, we design and do that, right? Of course, we do have the agile development processes that are very commonly adopted these days. And through those, you don't have the traditional steps as listed over here, right? If throughout the software development, a functionality or a bug or even an intentional functionality is added that can be taken advantage of in future, specifically when you have that application in production, then that can be a malware itself and kind of like difficult to be detected. The concept of software diversity as a software development techniques in which two or more functionality, identical variants of program are developed from the same specification, but by different programmers. Can you guess why we do this? Two identical developed applications coming from two different teams. You see it down here, right? So if an error is there, specifically if a malicious intention is there, can be figured out. Think about someone who develops an application for Bank of America, which in that application they can withdraw from other accounts. So if they can inject a piece of code, that piece of code goes in and deducts, let's say, 1 cent from each account in the United States and just pushes that to a specific account, no one is going to know something is happening because the software, the application itself, is conducting a kind of attack that is considered the normal functionality of that specific application, and hence possibly difficult to be detected. So the general concepts are, again, quickly going through these because mostly talking about software development for the cybersecurity focused IT guys is not really that fun, but we just want to talk about the topics. We do have the provisioning, which is the enterprise-wide configuration, deployment, and management of multiple types of IT system resources. Basically, a central system looking into every single step in from your development to the deployment and to the test and everything. We have the deprovisioning, and an application development is removing a resource that is no longer needed. Why do we remove those? Because those, if not needed, the concept of least functionality says, hey, let's remove it. We don't need that functionality. A very good example of the problems that can happen if deprovisioning is not happening is the log4j issue, which arose about December of last year, December of 2021. This is a logging module for Java applications, log4j, or log4j that was deemed to be vulnerable against security attacks. A lot of applications out there are not using log4j for their logging services, but the module is still in the application. It's unused, but it's in there. So that can be compromised. Hence, the deprovisioning can stop this from happening. If you don't need log4j, deprovision that from the application. Just remove it, push it out, and that's going to be creating the hardened security. Integrity measurement is an attestation mechanism designed to be able to convince a remote party that the application is running only a set of known and approved executables. So we want to move to Sec DevOps, talking a little bit more about this, which is a new concept. So an application development lifecycle model is a conceptual model that describes the stages involved in creating an application. Most projects use one of two major application development lifecycle models, either waterfall, as we discussed, or an agile model, right? The waterfall model uses a sequential design, as we talked about, right? And the agile model was designed to overcome the disadvantages of the waterfall model. Instead of following the rigid sequential design process, documentation, and all that, the agile model takes an incremental approach. Developers might start with a simplistic, very simplistic project design, start developing a small module in the application, test it, make sure it works, and then start building everything else. So rather than focusing on the process and documentation, agile focuses on getting the work done, right? Security DevOps is the process of integrating secure development best practices and methodologies into the process of development of an application using the agile model. Remember, here's the key word: using the agile model, right? So security DevOps applies automated course of action to develop code as quickly and securely as possible, which enables continuous monitoring, continuous validation, continuous integration, delivery, and deployment. And all of these are steps in software development, right? So SIG DevOps is often promoted in terms of its elasticity, basically flexibility or resilience in code development, and its scalability, which is its expandability from small projects to a very large project. However, the cornerstone of Sec DevOps is automation. Remember, without automation, Sec DevOps doesn't have a meaning really. With a standard application development, security teams often find themselves stuck with time-consuming manual tasks, while security DevOps, on the other hand, applies what is called automated course of action, as we discussed, right? To develop the code as quickly, as securely as possible. What I want you guys to note is when it comes to secure development of the code, there are many processes involved, right? And these processes should be used every time you develop an application to limit the data exposure, to limit the possibility of a bad actor inject the code in there, and finally to limit having a risky software in place, right? One of the things that are becoming important in there are actually incorporation of the encryption, right? And you want to have everything encrypted as much as possible. So the data should be encrypted in rest, in transit, and in process. So no matter where your data is, you want them to be encrypted. However, you guys know that data in process is extremely difficult to be encrypted, actually almost impossible, because processors need unencrypted information to work on, right? One other thing that we can do is ensuring that the memory management is handled correctly so that the stack overflow, buffer overflow, or anything like that cannot happen. One more thing that we can do is actually code testing. Just test the code before we actually release the code. And testing the code is one of the important steps in security DevOps, right? Testing should be performed during the implementation and verification phases of the software development process. Actually, some start testing in the design phase, like even when they're designing everything, they're testing the ideas to make sure this design is not going to have a flaw that can be abused later. So we do have two types of code analysis, static or dynamic. And the static one, you basically look at the code, make sure the code that you're going through line by line doesn't have any kind of vulnerability associated with it. And if you see any problem like log4j module is in there, just remove it. Dynamic code analysis is basically when you have the code developed and the code is running, you test the code. So fuzzing is used by dynamic code analysis tools and provides random input to a program in an attempt to trigger the exception. So basically we see the limits of a program, like something like a division by 0, right? Or calculation that is going to lead to infinity, something that can fuzz the program out, right? And we try to break the program. We try to add information to the program that can actually break the program. The other thing that you can do is conduct a pen test against the code. So run the application and then come out with your penetration testing team and get this application, get this web interface, get this local interface, on-prem interface, tested through invasive and non-invasive methods of pen test, which in that case, basically you can figure out the vulnerabilities associated there. As you can see over here, one thing that the fuzzing is doing is trying division by 0 to see what does the application do in case of a division by 0. Remember, the whole idea here is to push the application to its boundaries. Like if you want to think about a human being, to dynamically test a human being or apply fuzzing on that human being, what you want to do is you want to push them to the edge. What makes them super angry? And can I make them so angry that they turn vulnerable and I can take advantage of that vulnerability and such, right? So let's do a knowledge check. Help me with this. Which of the following best describes a static code analysis? Remember, you don't want to have a running code at this point.
So it's B.
Any other inputs? Anyone else? Actually, I see in the chat.
B.
I have a D in the chat. Anyone else? Okay. So the correct answer is B, right? Because in a static, we don't want the code to be running. And this basically is the manual process that happens through the peer reviews. So let's see what we did. So we went through multiple actually points throughout this lecture, which is longer than the previous one so far. We talked about organizations are pulling their experiences and knowledge gained about the latest attacks. They share that information in open source or closed source format, right? Providing threat intelligence, vulnerability databases, threat maps, and so forth. We talked about the steps that are being taken, and one of them, which is usually overlooked, is securing endpoint computers, is to confirm that the computer has started without any malicious activity. So the boot process is usually being neglected in the security procedures, and you want to have that in mind. that it is one of the most important ones, right? And you want to create that chain of trust. We talked about the antiviruses. We talked about the role and the degree of security that web browsers can provide. We talked about intrusion detection, intrusion prevention systems, right? We talked about how to secure OSS applications, and finally, we talked about security DevOps. So at this point, I'm going to go ahead and stop the recording.